our next plenary talk is to be delivered by Professor Shi-Min from Tsinghua University in China. Shi-Min is from computer science area. As you might have recognized, in this conference, we try to bring researchers from engineering, computer science, and mathematics. So we had Win yesterday from the engineering side. Shi-Min is firmly in the computer science side. Shi-Min is very well recognized in the computer science field and also broadly in China as well. Shi-Min is a fellow of Chinese Academy of Science, which probably arguably the most difficult academy to get elected into, given the population in China, and they only have around 800 fellows for the whole country. Shi-Min's research area is in computer graphics, computer vision, and deep learning. He has been working closely not only in the academic area but also with the industry. He is a director for Tsinghua Tencent Live. Tencent is a giant internet company which famously have this app WeChat. Almost every Chinese use it on their phone. So massive company. So he has been very successful in both academic research and industrial innovation. I wouldn't want to take any more time of you. So Shi-Min, the floor is yours.
So thanks, Chen-Feng, for a nice introduction. It's my great honor to be here. This is my first time to Porto, also as well as Portugal. So I'm very happy to be here. So my friendship with Chen-Feng can trace back to 25 years ago when he was a master student and I was a young lecturer. And then we have some cooperation. We published more than 10 papers on fluid simulation. So he is very strong in mechanics, and we computer scientists like animation. So we try to have a lot of cooperation. So today I'm very happy to join this conference because it's interesting to invite people from different areas together to discuss cooperation between different areas. So my talk is on 3D intelligent modeling from nerve to 3D Gaussian splatting, which are two very hot areas in computer graphics, also AI. So first, 3D modeling, past and present. So my main research area is graphics. Graphics is a field that focuses on representation, generation, processing, and the display of graphics using computers. So the concept of computer graphics was proposed by Ivan Sutherland in 1962, and he received the Turing Award, the highest honor in computer science. And so he is father of graphics. He is MIT. When he was a PhD in MIT, he proposed this concept, and after 15 years, his PhD student Alan Kai received the Turing Award again, but his contribution is on object-oriented programming and window-based graphic user interface. So we use computer, we use mobile. All such benefits are all because of him. He proposed concept of PC computer. And then his another PhD student, Katmo Clark, received the Turing Award again. But his contribution is 3D graphics and especially film production. So his another title is maybe you know the company Pixar. So he is first CEO of Pixar, hired by Jobs. So we can say computer graphics has transformed the form of computers and serve as a bridge between computer science and engineering applications. So today we have many scientists from engineering area. It's very nice. So in the last decade, the most significant feature of graphics has been the integration of AI in the computer graphics. AI has been widely used in graphics, different areas like modeling, rendering, video and image editing, even simulation, even animation and simulation also use AI technologies. So AI technology has brought revolutionary advancements to the application of computer graphics. And 3D modeling being one of most critical areas. So today we will focus on modeling. Modeling can be seen as a window to computer graphics evolution. So modeling serves as a cornerstone of computer graphics, enabling the creation of virtual world and the digital content, and forming the foundation of key applications like rendering, simulation, and animations. So in traditional 3D modeling, there are many types of modeling, such as sketch-based modeling. So you draw a sketch and the computer generates a 3D model for you. Or image-based rendering modeling, so you have provide a picture or several pictures for one object, and we reconstruct the 3D object. And the scan-based modeling, we use scanner to scan the object to obtain points or point cloud. Then we reconstruct the 3D model, geometry and material for the object. So then CAD modeling. So traditionally, computer-aided design modeling is a specialized form of 3D modeling that is widely used in engineering, architecture, and manufacturing to create detailed design and blueprints. So key features of CAD modeling include parametric design, so define dimensions and constraints, enabling easy modification of designs or your designs, and modular component support the creation of reusable parts, streamlining complex objects, and simulation capabilities, facilitating testing of design under real-world conditions, such as stress analysis or fluid dynamics. So CAD modeling has revolutionized the industries by enabling fast and more accurate design process. Some prominent applications include architecture, automotive, or product design. While CAD system has designed for accessibility, mastering professional modeling still demands specialized expertise and rigorous workflows. For now, the Internet's vast data has fulfilled deep learning, driving revolutionary advances in modeling techniques. So let's see an example. The integration of AI and graphics has broken traditional modeling concept. For example, if you want to build a 3D model, you at least for vision viewpoint, at least you should have at least two pictures of one object. For example, I take picture for this computer, this direction or that direction, two direction at least. Then with two pictures, you can compute the 3D model position coordinates by two pictures. But now AI changed. Now it's changed. We only provided a single image, we can reconstruct the 3D model. So with AI technology, it's possible to reconstruct 3D model from a single image, because with a 3D data set, we can train, and then you can reconstruct a model from single image, which is impossible in traditional idea, because its information is not efficient, not sufficient. So there is one very fundamental concept called the differentiable rendering. The introduction of differentiable rendering has achieved a breakthrough by combining rendering and visual reconstruction through neural network. So rendering, if you have material, lights, camera, setting, and geometry, you can use the rendering algorithm to obtain images. And in inverse way, if you have a picture, can we estimate the geometry, the depth, for example? This is a computer vision problem. So rendering is the process of transforming a model. A description of 3D object include the material, lights, cameras, and the geometry into 3D image. This is a typical problem in graphics. So the forward rendering process is typically non-differentiable. What's mean? So what is differentiable? Mathematically, we need a smoothly derivable. In computing, we need a gradient. We need a gradient. So since the emergence like N3MR and soft rasterize, two very famous algorithm, the forward rendering pipeline has been changed, become differentiable through approximate gradient computation and probabilistic rasterization. Then the rendering process now is differentiable. So with development of differentiable rendering, we can now obtain the gradient of forward rendering, and this enables us to update scene parameter through backpropagation. Backpropagation is a very important concept proposed by this gentleman, Hinton. He got a Nobel Prize last year. He also got a Turing Award several years ago because of his contribution in deep learning. He proposed this concept, backpropagation. So differentiable rendering has built a bridge from 2D to 3D, allowing us to directly optimize 3D information using 2D image, such as optimized models or camera parameters. So differential rendering makes the process from 3D to 2D differentiable, thus enable it to be integrated with AI technology. Let's see a very great work by Oxford. This is a best paper of CVPR 2020. And the CVPR, every year, more than 10,000 submissions. And only one best paper. So it's very, very excellent work. So by Oxford. So with only one picture of your face, this algorithm can generate 3D face. Then you can re-render the face to have another feature of pictures. So it's very powerful algorithm. So this is a very, very nice example of to show powerful of AI and combined with graphics. And some other very outstanding, very excellent examples. For example, we can use such technology, differential rendering. We can use single image to do mesh reconstruction, to obtain mesh representation of objects, and we can even to estimate the hand pose. So with the advancement of software and hardware, nerve and Gaussian splitting has emerged as novel forms of 3D representation. Both techniques benefit from the core idea of differential rendering, which optimize rendering process to enhance the quality and efficiency of 3D modeling. So my talk will focus on these two concepts and introduce some work in my group, and to show how you can use such very new idea, new software to help your research. I will show you some model zoo to you. So now let's move to the first part, first concept, nerve, neural radiance fields. So nerve was proposed in 2020 by several professors in California, professors in Stanford and Berkeley, UC Berkeley and UC Davis. So its stunning viewpoint generation effect has gained wide attention from the academia. So this paper already is only 4 years already attracted 13,000 citations. So it's a very popular paper. So what's the problem does nerve aim to solve? So input several images. If it's for a scene, you have several sampled images, and we hope to render normal views. You can generate other picture of other view. So this is, of course, if you can do this, you can also generate a 3D mesh representation, for example. It's also possible. So in middle of 2010s, view synthesis still based on classical geometry, like a Sigua paper in 2017. But nerve appeared as a representative of implicit field model rendering. The main idea of implicit field model is to take spatial coordinates as input and return its prediction through an implicit function. So input is the position of point in a scene and the direction of observing the point. And the neural network comparing only 4 connected layers and the activation functions, you can predict the RGB color and the density of points in such sample points on the line. So NeRF uses a neural network to represent 3D scene as a collection of colors and densities. So let's see this example. I'm sorry, you cannot hear the sound. So this demo just want to show the basic idea of NeRF. So let's skip it. So NeRF achieves more detailed scene geometry and better occlusion handling. So you can get such very beautiful results with several pictures. Then you can generate 3D effects. So then one of my PhD student, he published a paper in this direction. We call the recursive NeRF. Because the original NeRF is very slow for rendering, NeRF is equivalent to encoding the whole scene into parameters of a neural network, and querying the entire network for any position in the scene leads to low efficiency. So as the scene becomes more complex, the number of neural network parameters needed to increase, which makes the problem of slow rendering even worse. So represent the whole thing from a coarse to fine by recursive neural field. It maybe is a good solution. So we want to try to avoid the unnecessary computation to speed up the rendering by predicting uncertainty and existing earlier when uncertainty is low enough, and the dynamic growth of the neural network based on scene complexity. This is the main idea. So in recursive NeRF, proposed by my PhD student, each sub-network inputs coordinates of feature and the lines of a side direction D from the output of previous neural network and output predict color will give the following neural network, and output predict color, density, uncertainty, and features. So we involve the dynamic growth mechanism. In the initial stage, the neural network contains only one subnetwork. After a number of iterations, the points with high uncertainty are clustered. We use k-means for clustering, and the clustering method can be replaced by other methods. The neural network grows k branch according to the clustering center. K usually can be 2 or 3 or 4. And unlike NeRF, which output the color and the density of points in the last layer of neural network, recursive NeRF renders the final image recursively. The comparison of the reconstruction of effect based on large-scale 3D city, so very big scales. It's better than original NeRF, which fully illustrates the effectiveness of recursive network for complexing. So this paper is published in IEEE TVCG, Transcription on Visualization and Computer Graphics, in 2023. So then, when another student, Xiaolei Li, he published another paper on this topic. Feng Qiyuan, he published another paper on this topic. But his idea is to propose a novel 4D field representation to better fit into 4D space. So if the scene is dynamic, some moving objects, for example, then it is an automatically interpolation method by learning in interpolation ways by inner production and a time sequence that can be better decompose time and space information. So let's see a demo. So we can handle a dynamic scene. And this paper was accepted on IEEE Transcription on Visualization and Computer Graphics. So now let's move to another concept, 3D Gaussian splatting. This is a more new topic. Will nerve use neural network to implicitly represent a scene? It often struggles with slow rendering speed and computational demands. In contrast, 3D Gaussian splatting optimizes explicit Gaussian ellipsoid solids to represent a scene. So this paper is by some French colleague, and it is also very, very hot paper now. Only 2 years already, 4,500 citations. So 3D Gaussian representation, 3D scene as a cloud of colored Gaussians without any neural network involved. In essence, each Gaussian has a position of covariance, maximal density, and a color that describe local structure and colors. So similar to rendering with nerve, rays are cast from a virtual image plane through the scene. Each ray aggregates color from Gaussian kernel in the scene. The color contribution of each kernel is weighted by its maximal density and proximity to the ray. So overall, the 4 pipeline like below and 3D Gaussian use 3D Gaussian function to fit 3D space and use Gaussian mixture to complete rasterization. User can achieve normal view synthesis with those Gaussian net kernels. So 3D Gaussian splitting is a method that strikes a balance between discreteness and continuity. It achieves efficient 3D scene reconstruction and rendering through explicit representation and fast rendering techniques. You can see the results. So very, very nice results. Very fast. And then let me show one result of my student. So my student, Xiaolei Li, he published a paper in SIGGRAPH H last year. He proposed a concept called the DI scene. So DI scene uses complex long scene description with multi objects and their relation to generate 3D assets, represented with Gaussian splatting and with decoupled object and modeled interactions. So input we input are some text. You use large language model. So you input some language text, or you input a picture, and we can generate a 3D model, 3D scene, 3D models. So input are text or image. Output is 3D scene. So we use large model like GPT-4V to analyze its input text or image and extracted objects with their relationship as scene graph. Then the Gaussian reconstruction model generates independent 3D Gaussian representation from each object. Through two-stage optimization, we enhance each object's detail before intelligently composing them into a realistic, editable 3D scene. So AI now is very, very powerful, actually. So you can see results. So DI scenes advanced object decoupling enable sequential scene editing through condition statement and after initial generation. So you use text to generate a 3D scene. Then you can input more text to tell the system to modify to satisfy your ideas. So it's very popular, very powerful. So let's see an example. This is flexible input, decoupled objects, and accurate interactions. So let's see this very nice example. So you use some text or image, you can generate such movie. Okay, so actually we can use some text to describe some engineering thing. It's also possible. We did actually. So then let's to see another example for Gaussian splitting. This is some research work by my former student. This is a very interesting topic on deformation, especially large scale deformation. Is maybe some colleague from engineering area like this such topic. So for nerve and 3D Gaussian, all difficult for large scale deformation. Because for nerve and Gaussian, it's very time consuming and not deformal friendly currently, and the goal of research is to use Gaussian splitting for real time large scale deformation. So a previous method not nice because of artifacts, and we hope to improve Gaussian splitting method to do real time large scale deformation. The author of this research work, they optimize mesh-based Gaussian. So there are two key components. The first is phase splitting, adaptive refinement Gaussian optimization with mesh phase splitting guidance. So for some mesh, we split the triangle to 4 triangle, and then we use more Gaussian kernels. And the second is normal guidance, so optimizes the position of Gaussian around mesh phase normal to have better results. And deformal transfer, so guiding Gaussian deformation by use vertex position and deformation gradient in mesh deformation method, so we can have very nice result. So I think this topic is quite interesting and very useful for some engineering applications. So this is an example. So the paper is by the first author is my former student now in Institute of Computing Technology in CIS, and the last author is my former student. Now he is a professor in Cardiff University, UK. Okay, now let me show some software which is quite useful for your research and developments. Today I mainly introduce two main important concepts, nerve and 3D Gaussian. And to enable rapid programming with deep learning, we developed two deep learning model zoo for nerve and Gaussian. Use the deep learning framework Jitter. Jitter is a framework developed by my group, which is similar to PyTorch or TensorFlow. Very similar, but Jitter is by my group. So we open sourced in GitHub. You can download and very easy, and you can use those two model zoo. And for GNerve is a model zoo for nerve. We analyze existing nerve methods and summarize the main training process of nerve into following 7 parts, and decoupling between different parts allow for easy invocation and replacement. And the paper is published in Computational Visual Media. Just a short paper for this model zoo, and being the first, this model zoo is the first deep learning framework to support instant NGP. It achieves remarkable nerve training in just 5 seconds. Before this famous algorithm, it usually needs 10 hours for training of a nerve model. And furthermore, it supports 6 representative nerve models, include very famous like news, like MIP nerve, for example. So if you want to use nerve for your research, you can download and use this model zoo. And another model zoo is J-Gaussian. So Gaussian for JIT. The J-Gaussian model zoo supports methods such as MIP splitting, 2D Gaussian, 3D Gaussian, to efficiently accomplish tasks like novel view synthesis and object reconstruction, achieving a training speed 1.2 times faster than PyTorch. So use jitter, you can have much more efficient. And so if you like such idea for your engineering application, you can remind your student to install jitter, and then you can download those model zoo. Then you can immediately use those software for your research. Very easy. So jitter, we use jitter. So jitter is a deep framework based on meta operator and unified graph execution. So let me introduce jitter a little bit. So jitter is a deep framework like a PyTorch, like a TensorFlow, but we use two very new idea. The first idea is that is a meta operator. You know, if you use PyTorch, your students should be very familiar with PyTorch. So PyTorch provided more than 700 operators. Use operators, you build a model, then you use that to train the model. Then you can do inference of the model for your applications. And if you use TensorFlow provided more than 2,000 operators. But in our jitter framework, jitter deep framework, we have 18 meta operators, and as all other machine learning operators can be fused by those 18 operators. So what's the benefits? For example, we have some new chip, new GPU in China, because American government don't allow to sell GPU to China now. So if we have a new GPU, we need to, the engineers in the GPU company need to implement it, all operators on the GPU. It's very time consuming. So for new GPU, it requires 100 engineers for 1 year. But if you use our jitter framework, only one student, 2 weeks, because we only need to implement it 18 meta operators on the GPU, then all operators can be run automatically. So this is really nice. And the second idea is called unified graph. You know, for TensorFlow uses static graph. It's efficient, but it's not flexible. And the Meta, Facebook, use dynamic graph, which is flexible but inefficient. So jitter, we call the unified graph. We try to combine benefits of two framework, TensorFlow and PyTorch. We use dynamic graph, but we decompose the graph to several static subgraph. So, and when we optimize the model, we try to represent the operator by meta operators and optimize in meta operator level to achieve more efficient results. And we have open sourced a lot of models, other model zoos. For example, computer vision, segmentation, detection, point cloud, and like medical image, for example. So many models develop open sourced. So if you install jitter, then you can use those models for your research, for your applications. And most important, all research, all application area, model zoo of jitter is much more efficient than PyTorch is. For example, computer vision task usually 30 or 40% faster than PyTorch. If you do GAN, average 1.26 times faster. So it's quite very efficient. And the jitter support to heterogeneous computing device. So we have a lot of GPUs, different kind of GPUs in China. So we try to let jitter to support all kind of GPUs. So benefiting from the meta operator fusion strategy, jitter can easily support a device of different programming architecture, include C++, CUDA, LookM, OpenCL, BAN, ACL, etc. So we can support all different kind of GPUs. So conclusion. So today I mainly introduce NeRF and Gaussian splitting, and also I introduce softwares of those two important concepts. And both two methods are point-based rendering method. So what's their difference? So opacity modeling. So in nerve, opacity is derived from density value, and in 3D Gaussian splatting, opacity is an inherent property of each Gaussian. And for rendering method, nerve require dense sampling around ray, and 3D Gaussian splatting does not require sampling. It's only needed to determine which Gaussians project onto which pixel. So the integration of AI and 3D modeling holds the promise of boundless development. As we stand on the brink of the new era, the convergence of these two fields is already given rise to transformative advancements, such as intelligent design, efficient production process, personalized customization, virtual reality integration, and cross-domain application expansions. So let's have a better future. So thank you for your listening. Thank you very much.
Thank you, Shi-Min, for the exciting plenary talk here. So we open the question. We got time for questions. So, any questions?
Very nice talk. So, for my understanding, would be you take for first part, you take one photo.
Yeah.
You can generate three-dimensional.
Yeah.
But if you just take one photo, static.
Yeah.
You don't see the back side.
Yeah.
How can you predict the back
side? So because we have a lot of data, so use data to train a neural network. So it's a prediction, maybe not correct, but give you some results. Yeah.
So basically, you have a database.
Yeah. For example, for face, different people have different face, but the structure of face are basically similar. So if I have thousands of face in a 3D model, I scan the head of people and I take picture. So 3D scan data and 2D picture, then I train the neural network. So if you have given me a new picture, I can estimate a 3D head, for example.
Database,
yeah, of course, yeah. AI need data. Data is a key part of AI.
Okay.
Yeah.
So now that is a three-dimensional system. Now you go to 4D.
Yeah. 4D is for dynamic scene.
It's a dynamic.
Yeah.
So you need to take.
Yeah. For example, robot is walking, for example, and do something.
But the thing will be, it really depends on the object, right?
Yeah.
So this is a lot more like in mechanics we call rigid body motion.
Yeah.
Right? Like your say. But the problem would be if it's a flexible system.
Yeah.
You don't know how flexible the system is. Do you have a database on that too, or how do you do that?
Yeah, for AI applications, usually for specific task, you need a specific data set. Of course, yeah.
So
but
you do have a database for flexible structure? Or,
yeah. So
it's only for rigid structure.
Yeah. So if you want to use AI ideas in a factory, for example, of course you need to cooperate with such factory and obtain a lot of data. Then you can train. Yeah.
Okay, thank you.
Yeah, thank you. Hello.
Thank you for a very fascinating and enlightening talk. It's amazing to see how you have improved the performance using jitter. If I remember correctly, you said it was 13 meta operators that you are using.
18, yeah.
Oh, sorry, 18,
yeah.
Yes. It would be very nice if you could tell what each of those 18 are actually doing.
Yeah.
Could comment on what is it that has enabled you to actually make jitter more efficient than PyTorch and TensorFlow. And then also the zoo that you have is interesting, and I in particular liked the video where you were zooming in and zooming out on the bicycle wheel. So is there any of the models in your zoo that is optimized for doing video editing? Would be
let me show you what
language vision model.
Yeah. Let me show you.
3 questions.
Yeah. Let me answer the first question firstly. So I'm sorry, it's in Chinese, but the picture is so we have 3 kind of meta operator. For example, the first kind of operator is one to many. For example, if you have a vector, and you put the vector 4 times to have a metric, this is one kind of meta operator. We call the broadcasting. So one vector, 4 vectors together, then like metric. And this is the first kind. So one to many, one to several kind of. And another kind, for example, I have a metric, and I compute the sum of the I calculate the first row. 1, 1, 1, so we have 3. So from metric to vector, this is the second kind of operator. So we can, this is, and the last kind is two element to one element. For example, 2 vector, we compute the sum of to have a new vector. This is, so we have 18 such kind of meta operators. And the very interesting property is that, so if a neural network operator be fused by those 18 meta operator, its back propagation can be also represented by those 18 meta operators. So this is a very important necessary mathematics property. So this is your first questions, and please, I'm sorry, what's the second one?
So the second one was if you could please shed light on what it is that really enable you to improve the efficiency compared to TensorFlow and PyTorch. What are like the main items that gain you speed and reduce computation by each of them?
So we are much faster than PyTorch. So why we are so faster than PyTorch? Because of the meta operator issue. So when you use AI deep learning, for example, in frame, we write code. We write code in based on a deep framework, and sorry, my son is calling me, but
well, please answer him and tell him that you are here giving a plenary.
So if you want to let your algorithm much faster, your framework much faster, you should do a lot of optimization. So let me then maybe it's better to show a picture to then we can make it very clearly. Let me maybe use this again, and so I'm sorry, it's still in Chinese, but so for artificial intelligence or deep learning, the most important thing is this picture. So you input a picture, and you want to analyze the picture to have segmentation results. So the main idea is you should use operators to design a model. A model actually is operators together. Then you have a model. Then you use data, a lot of image to train this model. And then you train the model and compute all parameters of the neural network. Then you can do inference. So this is the main idea of AI or deep learning. Then in our deep framework, we decompose this called the computer graph, computing graph or computational graph, and we decompose the computing graph to static subgraph. So if you want to change, for example, here you want to change for PyTorch, you can change different operator. But the TensorFlow you cannot. You're not allowed. But for our framework, you can change. It's flexible, but the place you don't change, we regard it as a static subgraph. So we have subgraph, and then we decompose all operator to meta operator. Then we generate C++ code from those meta operators to have C++, because C++ is much efficient than Python language. Then we use some optimization method from operating system. You can see operating system, for example. You have a lot of technology to optimize. Then you finally run it on different GPU. So it's quite complicated. But the main idea is the meta operator. This is the main core part of our framework and why it's more efficient. Yeah.
I understand. Thank you. So, do you have an efficient method for converting PyTorch and TensorFlow models over to the GTOR model framework?
Yeah. So in China, many companies or professors or research lab use AI, do research of AI, but 5 years or 3 years ago, for example, we all use GPU, NVIDIA GPU, but now NVIDIA not allowed to sell in China. So we have to develop our own CPU in China, right? And then we hope to, so if you can imagine, there's a company, Chinese company, it's a manufacturer company, for example, and they use NVIDIA GPU and use PyTorch to do their products, but now no GPU again. But a lot of software developed already based on PyTorch. So we help them. So you can how to say 插件，我们叫插件 plug-in, yeah. We write a plug-in, and if they can install PyTorch and install Jitter, also a plug-in. Then they don't need to change any code. Can automatically run on Chinese GPU. This is so we do something like that, yeah.
So time for one more question.
So with the different version of PyTorch, for example, Google, they rewrite the PyTorch with Google JAX, which is 14 times faster.
Yeah.
So the speed, it really depends on the hardware. And software.
You're right. Yeah.
So when you say you have 2 times faster, now, but maybe 6 months later it will be.
Yeah. So we should always change, always run faster. Yeah. Of course. Yeah.
So these are written by C++ included.
Yeah.
Okay, so I'm cautious about the time. Shi-Min will be with us for the social program after lunch. If you want to grab him, feel free to do so. So let's thank Shi-Min again for the plenary talk.
Thank you.